All right, I think we'll go ahead and get started, and folks will trickle in, or maybe if the talk's bad, trickle out, and that's just the way that it goes. But thanks for coming, and today I'm going to talk about a journey that we've been on for the last 8 years, really looking at operationalizing and working with ozone, and a particular form of ozone in form of nanobubbles, and the little journey that we've been on. So I'll do a couple little vignettes to get us all on the same page. And my name's Athey, and I'm the co-founder and CEO of Zeroic. All right, let's start with ozone. Probably everybody knows, but ozone is just 3 molecules of oxygen. We sometimes just call it supercharged oxygen. The oxygen we breathe in the atmosphere is 2 molecules of oxygen, and ozone is just a gas. So it's been around for a while. You can smell ozone in the atmosphere when there's a thunder and lightning. The lightning oxidizes some of the oxygen in the atmosphere, and you smell ozone. Ozone is one of the strongest oxidizers compared to the normal chemicals that we're looking at in food safety, whether we're looking at a peracetic acid or a chlorine dioxide. Just the amount of energy that's bound in that third oxygen molecule that's bound to that ends up being able to be a very strong oxidizing agent, and it'll go end up and lyse the cells and destroy the cells that it comes in contact with. It's incredibly strong. You don't need a lot of contact time where you do with chemicals, and it's incredibly powerful. And frequently, ozone is used in wastewater treatment plants where you're bubbling a lot of ozone into some sort of industrial process. Ozone hasn't worked for food safety. So there's a number of systems that are out there. They sort of work. They have issues. And most often the issues are you can't overcome the organic load that's in the product that you're treating. You can't deliver enough ozone to target to do the job that you're trying to do for the delivery of reduction of pathogens or microbial load. And so the challenges of ozone have fundamentally just limited its adoption. But it's a magical thing once you can get it to work. All right, so that's vignette number one, sort of on ozone. All right, nanobubbles. So let's talk about bubbles. So there's the normal bubbles that we have, right? And I brought props, of course, so we have bubbles, right? And so the bubbles that we have are sort of normal bubbles, and we interact with bubbles, and we think about them when we put some gas into a liquid. A lot of that gas comes out of that liquid as it sort of rises to the surface. There's some new features and new physics that's been discovered around the 2000s, and I'll get into the history in a minute. But the bubbles we're talking about are very small. They're less than the wavelength of light, actually. So light is normally about 600 nanometers big. An ultrafine bubble or a nanobubble is about 100 nanometers big. And this gives some relative size scales for all of these things. And we'll talk about some of the amazing features of nanobubbles after we get through the sort of the discovery phase of the discovery of nanobubbles. So they've always existed, right? But we didn't know they were there for many, many years. And so there were some early reported observations of nanobubbles in ocean waves. Things were crashing, and you could detect some sort of ultrasonic method from looking at these, and they were assumed to be transient. There's actually a theory of how bubbles work, and nanobubbles shouldn't exist. And so this is one of my favorite facts about nanobubbles, and it allowed for a certain number of things to happen where academics were fighting about whether they were real or not, and the practitioners went into the field and started making things. And so this was a very fun sort of empirical field in the early 2000s. And a lot of this took off in Japan. And what fundamentally happened is we increased our ability to measure things, and we were able to measure sort of the density and scattering of smaller than light particles and look at those in solution. And we discovered that there are these things called nanobubbles. So there's a bunch of interesting things about nanobubbles and their discovery and their history. And a number of things are still not solved. But we know they exist. And here's where it gets interesting. So a macro bubble, you just blow in a bubble at the bottom of a straw, and the gas comes out of the liquid. Sometimes you see like a cloudy white if you work in a or you go to sort of a rural environment and they're pulling water from a well, sometimes that water is really gassy and it clears up after a minute. That's sort of a micro bubble. And the nanobubbles themselves, the amount of gas that's in there is less than the buoyancy force required to have it come out of the solution. So the nanobubbles stay in solution forever. And so the ability for us to embed gas into liquids all of a sudden starts looking really interesting, because now we have something that doesn't float to the surface, and we can start changing some amazing properties about the liquid or the gas that we're delivering. And so the nanobubbles themselves don't float. They're stable in solution for a week to a month in the solution itself. And we can now put in 10 times the amount of dissolved gas that we used to be able to, that were sort of fundamental laws of physics. And I say this as a physicist, so I'm not making it up. And we can change the density of the liquid itself. So for flotation separation processes, you end up opening up the water matrix and having a better processes for dissolved air flotation and other sort of processes for settling. And so we have all of these amazing things that nanobubbles can do. It's not magic, but it does fundamentally change how we think about gases and liquids interacting. So that was vignette number 2 on nanobubbles. And we'll talk about how all of this pulls into food safety here. As we come down, and there's now a lot of applications that are starting to deploy nanobubbles, and there's a small number of companies that are looking to do this. We're the only company that is doing this for food safety, and very specifically for food safety. And so in 2018, we saw these sort of opportunities, and a unique set of individuals came together. A scientist, a lawyer, and an MBA with some expertise in understanding the agricultural workers and the problems. And we started writing grant funding to see if this would be an interesting idea. And we founded a company called InSolution. InSolution spun out in 2026, the company Zeroic that we're talking about today. And InSolution received something like $6 million from FDA and USDA to prove this technology out. And so we're in 6, 7 different universities, have validated technology, have pushed that through trials, and have really validated. And now we're at the stage where we're commercializing this opportunity through this vehicle, Zeroic, where I'm also the CEO. So Zeroic. We named the company Zeroic because the food safety professionals are on this heroic journey to chase zero, right? And you all know this. And zero is never enough, even if you get a bunch of zeros. And there should be more tools and more technology to support this. And so this is really our quest, is to provide a tool in that and recognize the heroic journey that it is to go chase zero. And to be able to do it without zero chemicals is kind of amazing. So we have this unit. It's about the size of a refrigerator, and all the inputs are compressed air from your facility, electricity of 120 volts, and water. And we'll turn that water into sanitizer. And we'll put that unit will put out probably 20 million gallons of sanitizer throughout the course of its lifetime. And we like to say the training manuals push the green button, which is all you have to do. And then all of a sudden, you're able to clean surfaces and food, and what else do we clean? Everything, whatever's dirty. Hands, people have asked, hand washer, boot washer. We've looked at a lot of different opportunities for rolling this out. And one of the unique things about ozone is that it has the FDA GRAS designation. It's organically approved, and it decays back to oxygen and water. So there's no residual left on the product as it goes out. So as we mentioned, there's some remarkable features about nanobubbles, and now what we're going to focus on for the food safety is really the ozone. So the ozone and the nanobubbles come together and sort of solve the unique problems that have prevented ozone from being used as an effective antimicrobial for food safety applications. And so one of the things that happens in a food processing plant is you've got a lot of individuals surrounded around in sort of a pack house or something like that, or a processing facility. And the ozone that, in traditional legacy ozone that was around, would come out of solution, and then you would start getting sort of harmful worker engagements with the gas that's coming out of the solution. With the ozone nanobubbles and the way that we're able to deliver it, we're able to deliver 10 times the concentration with 100 times less off-gassing. And so that really enables the ozone to finally work just through the exploitation of this new science feature of the nanobubbles. And so we're looking at a safe delivery. The nanobubbles themselves have a slight negative charge, and so they push away from each other and sort of have a homogeneous distribution throughout the liquid volume. And so you can go and clean the bottoms of tanks as well as you could the tops of tanks. Traditionally, ozone would rise to the surface and there would be a gradient. We're able to sort of pump and push that liquid far throughout a plant, up to a couple hundred feet, and we improve the efficiency of the entire delivery system. Because we built this in a modern way and we wanted to do it to support all the food safety professionals that are out there, we did it with a lot of digitization. So there's something, I can't remember, it's something every 5 seconds we digitize something like 200 data points, and we store all of that and collect all that for verification of process. And then at the end of the day, the food safety professionals that we're engaged with will receive a report that helps with your audit and compliance and satisfaction. It also helps on the maintenance sides to understand what's going on inside the machine for any remote troubleshooting. All right, so my challenge as a CEO is I have to sell something that's invisible. And so I have a video here, and what I call this is the most amazing video of nothing. And so we'll play it and we'll talk about it. But so this is 7.5 parts per million. And 40 parts per million of oxygen coming out the end of a hose at 15 gallons a minute, and it looks like I'm not doing anything, right? And we zoom in and we see some macro bubbles that have aggregated from the nanobubbles, and so we're pushing out an incredible concentration of solution, and so we're constantly thinking about how do we make visible an invisible process, because food safety is really about an element of trust too. Where you have to sort of trust that the process is working, which is one of the reasons we worked on all this digitization. So that was one video of nothing. Here's 2 more videos of nothing. So the top video is in a leafy green processor up in the Salinas area. The bottom video is an apple cider facility washing apples. And we're, on each of these, we're pushing out about 4.5 parts per million of ozone. And we're in the big, cavernous rooms. And we're measuring the ambient ozone that's coming out of the solution, out of the liquid. And on this one, we're under the spray bar. So we've replaced their PA as an overhead wash for their incoming apples. And we're underneath that now and measuring the ambient ozone. And we're well under that there's a limit for OSHA required standards and ambient levels at 1/10 of a part per million, and we're well under that. Okay. It wouldn't be a food safety talk without a lot of log reduction discussions. And so a lot of the next of these talks these next slide sections are in a few different categories of water, biofilms, and product and surfaces, food contact surfaces, talking about the various trials and tests we've done, either in laboratory inoculating with Salmonella, Listeria, E. coli, or in actual processing facilities where we're using indicator organisms most often. So the very first test we did, because we were worried, you put the gas in the nanobubble, how does it come out and go interact with the pathogen? We were worried that we were going to lock up all of the ozone. The new form of this gas encapsulation with the nanobubbles was going to lock up the ozone and wasn't going to allow for the inactivation of pathogens. And so we did a 5-pathogen cocktail strain. When we did this with E. coli, Listeria, and Salmonella, we put in 1/2 part per million of the nano ozone, and the ORP readings are off the charts, of course, and we get log 7, log 5, log 4 kill that equalize the total wipeout for the inoculations. And this makes sense. You can kill things in water with ozone. And so, but we wanted to prove to ourselves that the nano ozone didn't somehow lock up that ozone and have it not be available. Each one of these slides will have sort of our research partner. Those are all externally validated and some aspects of the study and key results. We do really well on spores too. This was looking at University of Alberta, looking at in proxy for a meat processing environment, looking at reductions in a Pseudomonas. One of the things that happens once you start changing out your chemicals for non-chemicals, particularly the ozone, is you start improving other parts of your process. And so this was the apple cider facility, and what they had a land discharge permit to spray some water on some Christmas tree farms out in Michigan, and they could only do that if their BODs and their holding tanks were below 2,000 milligrams per liter in BOD units. And so and what you do when you add chemicals to your entire system is you're chewing up the bugs that are doing the work, that are processing the organic load on the way out of the plant. And so the more of the ozone, the more of the water we replaced in the facility, they were only using about 30% of their water on their spray bars. The better the BODs got on the effluent, and we've since shown that we actually made more problems for them because the water was too clean, and then they had some other issues. So we're working through them with that, but the concept of replacing the chemicals has many intended beneficial consequences upstream and downstream, in addition to just sort of doing the same job as the chemicals. We're also working in outdoor growing environments and more challenging water matrices. And so this is some work we've done with the University of Arizona. This is in seeking compliance for the FDA's new ag water rule, where you have to treat water before it goes overhead. And we show that we can do this in a complex dirty matrix under various pH scenarios. Here we're looking at large volumes of water and a comparative study of treating water with a Sanidate or PAA or a UV system in the ozone, pulling that water out of a canal, cleaning it up, and dumping it onto leafy greens that are going to be harvested. In the last study on the water category, we worked with USDA directly at Beltsville, Maryland, and we were looking at proxies for Cryptosporidium and Encyclospora. And we're seeing very interesting results in the reduction of sporulation. And so the main point in sort of all of these studies is that the ozone is incredibly strong at destroying all of the things that we care about, from S-Tech all the way to Cryptosporidium. Next, I'll talk a little bit more about in-plant processing. We sort of diverted ourselves there for a minute, talking about outdoor ag and water, but just to showcase how much versatility there is in the system and the technology. And so one of the other interesting things about nanobubbles is they act as sort of physical scouring agents. And so if you run them down a pipe, it'll break up biofilms on the insides of the pipes. You don't have to use ozone inside of that. You can use any gas. And so any gas that runs down a pipe, and this has been proven in many published academic studies, the nanobubbles will end up scouring and breaking up biofilms, breaking them off, and delivering cleaner pipes. There's another interesting aspect of that is the nanobubbles themselves, like any sort of the bubbles themselves like to bind to surfaces. And so on the surfaces of the pipes, the bubbles end up binding and forming a protective layer to prevent the future growth of additional biofilm. And we've been able to show that this result gives you about another day and a half before you would reach the same sort of bio-level growth on a biofilm. In terms of removing biofilms, we've done a number of studies. Washington State University did a great study. I'll zoom into that here in a second. But really showing about this combined effect of getting particularly on biofilms. You get a physical scouring effect, and then you also get an effect from the ozone. So what we did in this study was we looked at a 7-day Listeria biofilm on a stainless steel coupon, a pretty tough biofilm. And we did 2 different levels of studies with 2 different methods. And so one of them, we just put in oxygen nanobubbles, so no ozone. And then we just sat that stainless steel coupon in that bath and looked for the log reduction as compared over water. We got about a 1/4 log reduction just from the oxygen. If we started stirring that, we put a stir bar underneath it, we got 1.5 log reduction just from the oxygen nanobubbles, so no oxidative effect. Next, let's just add the ozone to this, the experiment. If we just have the ozone, we get about a 1.5 log reduction of the 7-day Listeria on a stainless steel coupon. And then if we move that liquid, we get an additive effect, and we get a 3-log reduction on a Listeria biofilm on a stainless steel coupon. A very nice little compact study done at the laboratory scale, confirming a lot of the things that are seen in the field on indicator organisms. This is looking at we had a deep engagement with a pork slaughter facility, and so we've been in beef slaughter and also in poultry processing. And on the carcass wash, looking at something like, I believe it was 500 parts per million. This is peer reviewed and published. Looking at carcass wash for a PAA wash on carcasses hanging last step before chiller, we're looking at about a 1.5 log reduction. We got the previous year's worth of data. We then went and did 10 samples using the ozone nanobubbles, and we're getting a 3-log reduction on a similar population of product going in. And so sometimes this can be incredibly effective, and I tell my team you have to think like a bubble. You have to think like a bubble in order to understand how to apply it to get the right answer, or to optimize for a better outcome from an antimicrobial perspective. Poultry processing, in that thinking like a bubble, when conditions are right, we can do just as well as chemicals processing on poultry parts, which is some of the more challenging aspects in food safety. Poultry plants, we've been in a good number of them, proving out a number of applications where we're really looking to, you do have pathogens and the salmonellas come in there, and looking at getting those presumptive positives driven to zero. A study we're doing right now, we're looking at ground chicken, where you would expect, just because you're comminuting all the meat, that your positivity rate's going to go up. In the first 2 months of this study, we dropped a sort of standard process of 34% positive down to 8% positive, made some additional processing step recommendations upstream, and drove that third of positive rates on the ground chicken down to 0. The next set of the samples, we'll talk about our food contact surfaces. Really those zone 1s, we love those zone 1s where it's conveying stuff. We love working on interlock belts. We love working on complex machinery, because there's some benefits that we can see, and we'll show in the data, where the nanobubbles are penetrating into the surfaces and cleaning in a way that even deep cleaning has struggles with. So we had the perfect sort of A-B study. We were at a pork slaughter facility, and half of the hog went left and half of the hog went right. And in that study, we started halfway through the day and then ran through the rest of the shift of another 4 hours. And the ozone nanobubbles are cascading down to 0 by the end of the shift, and the other belt is getting dirtier, and the spread at the end of that is 2.5 logs. We see this again and again and again, and we just knock it out of the park on food contact surfaces. This was sort of the previous year's day, previous year of twice a day, 3 times a day sampling on belts, sort of average. We went and put just a little bit of ozone nanobubbles in a dip tray where the belt, as it curled around on the back way, we pulled out a roller, let that belt sag down, put it through a replenishing amount of ozone nanobubbles. We're 1.5 logs cleaner, and we're actually very close to 0 on those during operations. This is what I was mentioning in terms of the deep cleaning. This was an interesting study that we did where we drove apart an interlock belt and we did swabbing in between. Don't do that unless you want to find things. So we swabbed in between these belts, and then we did our dip and roll for a single day's worth of processing. And when we came back the next day, it was 2 log cleaner on the belt we were testing on, and the control belt maintained sort of a 2.5 log. Interestingly, this was the only place in the plant where we found Listeria. It was not Listeria mono, thankfully, but these are the places where things hide, and the nanobubbles do an incredible job on food contact surfaces. I'll show one more of these, and this was another interesting one. We were out in Central California processing. This was first contact surface in to the processing facility from a spinach and mixed greens facility. We cleaned that first belt, and the during operations, we were cleaner than their pre-operational numbers. And so it gets cleaner as you go. I had a customer in Bakersfield recently tell me she couldn't believe that it was true that the longer they used our product, the cleaner their stuff got. And so there's an interesting firewall effect too, where we've got two belts here. One is sort of the dumping belt that's running along, and then there's an incline belt. The second belt was 4 log cleaner the next day when we just cleaned the primary belt. And so there's good reasons to sort of put up these sort of firewalls in your facility if you're doing sort of thinking about extended runs or running with processes that add a lot of matter and organic load to your facility. So in short, we believe we solved ozone. Ozone was not working. We believe we have a solution now for addressing certain things. We believe we are equivalent on product, where we're going and washing and competing head-to-head with high parts per million of PAA. I believe that we're better on surfaces due to a couple of the aspects of the nanobubbles where we can keep in operations a facility at their pre-op levels. When we think about turning sort of sanitation or operational sanitation into a strategic advantage, we have to think about how is this applied. And this gives us new techniques and because of its benign nature, because this is staying on surfaces and you don't have to regulate it or label it, we have the opportunity to clean more of our surfaces for longer throughout the processing, and you can extend those runs and produce more product over a given course of 24 hours or 72 hours. Those are the slides I have. I can shoot the bubble gun again. And I would love if anyone has any questions. It's a lot to take in, but this was the last 8 years of our journey, and we're happy to share it with you guys. Thank you. All right. Question?
For the operational slides that you showed, did you have to do any physical removal of the organic matter before you applied your solution, or was it just like if running and it went to break and you sprayed it and yeah?
So this now John's starting to think like a bubble. So anyway, so the question is how do you apply it? And very often we have to come in and help everyone think like a bubble. And so for that particular application, we applied it during operations, and so it was just running all the time at a very low sort of trickle rate. But there was no need to like stop the line, clear the product, spray down, or anything else like that. You don't have to do that if you have a solution that's continuously cleaning.
I'm curious if you can, if you have any comments on the tendency to degrade the nutritional value of food. And I'm guessing there are some nutrients that are pretty inert to ozone, and other nutrients, maybe valuable lipids, for instance, that are subject to nutritional degradation.
I don't know specifically with regard to any specific nutritional elements, but I do know that consumers are dying to know what's their food has been exposed to on the way to market. When I tell everyone that triple wash lettuce has been washed in swimming pools versus chlorine, they're like, no, but I buy it from Whole Foods and it's organic. And I was like, no, it was washed in a lot of chemicals. And so there is a chemical-free movement that's a little bit tied to sort of the MAHA movement. And I think this has a play in that because it is chemical-free. I think any oxidizer is going to go and interact with the food. The nice thing about our unit is we can set the concentration exactly. And so we can say, hey, you want 4.2 ppm because you understand that's where the fat starts oxidizing. Above that, we can deliver that.
One individual told me, and not really in the most scientific way, but he said, oh, cooking is going to destroy sort of half of the nutritional value, and ozone will destroy maybe 1 or 2% of it. But I've been stimulated by that comment ever since, but not really knowing any basis.
Dr. Al, do you know?
I think before we worry about nutritional value, let's keep ourselves alive first, because this will kill the bacteria that, you know, kills us, and then let's worry about the nutritional value after that. That's my opinion.
Yeah. Jeremy.
In your presentation, you talked a little bit about the penetration effect into the surfaces. Could you unpack that a little bit?
So penetration into surfaces, like we love those interlock belts. We love cleaning those. And the nanobubbles themselves, as I mentioned, they all have a slightly negative charge against each other, and so they push each other away. And so there seems to be an ability that where the bubbles can sort of penetrate in and deliver that ozone into the surfaces. And I'm not sure the mechanism is exactly known why that would do a better job than just water. But you are delivering that in there. You do have that physical scouring effect, which is real and measured and well documented. So it could be the combination of that smashing in there breaks up some of your stuff.
You're right. I mean, the bubble has negative charge, and the ozone ion has positive charge. So the bubble carries on the ozone ion on the surface, and since they have so many surface areas now, and they can go to deeper cracks, either on surfaces or on the surface of the lettuce, that's where the effectiveness goes through.
Thank you.
Hi, I was just wondering if there's any positive effects as far as pre-op / complete teardown of equipment. Have they noticed that they haven't had to completely tear everything down because it's affecting it all day long?
So just like with any oxidizer, you have to be careful of your materials. Like, so ozone will go eat burn a rubber, but Viton is fine, and many facilities are already switching to something like that. Maintenance and operations love our technology because it makes when they do have to work on that equipment, it's clean. And so they don't have to scrape the grease off or everything else. And the equipment seems to run smoother for longer when it's clean all day long. And so we've seen beneficial effects from applying this just because it just keeps everything clean. It's like oiling the hinges, essentially all day long. I really appreciate everyone coming. Nanobubbles is super interesting science. We've been honored to sort of get to work this and happy to share it with you guys. Thank you.